Well, thank you very much, Jürgen, for the introduction. Thank you, Richard, for the invitation as well to give a talk here. And thank you all for coming this afternoon session. I noticed that the name of the workshop here is quite interesting. It's Bridging the Gap, Transitioning from Deterministic to Stochastic Interaction Modeling in Electrochemistry in general. So I used this to motivate a little bit of this kind of picture that I wanted to convey about stochastic modeling in atomistic simulations, especially. How would we go about bridging these gaps between atomistic models and continuum models? And how would we go about thinking of stochasticity in materials modeling in general? Just to start with this, of course, you can see here I'm from across the street in the Department of Material Science and Engineering from UCLA, and as a material scientist, we like to think about everything as a structural property relationship, right? In general, we know nowadays, and this audience knows very well, that there's a very well-defined pathway between structures and properties. Perhaps it can be challenging, but often it's straightforward to think about properties given structures. Less straightforward it is to think about structures given properties in this inverse design or inverse modeling approach that is quite promising one in the recent years. However, when you think about structure-property relationships, this doesn't tend to be enough to describe the entire paradigm of material science and engineering. We know that materials have to be synthesized. So even if you provide an experimental colleague, someone with an experiment with a structure that you want to have synthesized, there's a lot of unknowns here in the space of synthesis. For example, what are the mechanisms of synthesis? Are there any predictive models to do that systematically? How do we handle out-of-equilibrium theories, and how do we explore these combinatorial spaces of synthesis conditions? And on the other side of the spectrum, properties are not just static outcomes of structures. They have a particular performance, something that degrades over time, has a particular lifetime, and you have a range of properties that give rise to some uncertainty over your material's performance. So I like to live in these two sides of the spectrum, the synthesis-structure relationship and, of course, the property-performance relationship. And when we think about synthesis and structure, it relates very closely to the questions that this community in the electrochemistry likes to think about as well. For example, when we think about synthesizability of materials, the kind of picture that we usually think of is one in which you have a phase diagram. The phase diagram is incomplete because you don't have knowledge of all of the phases and metastable phases that might be accessible given a certain set of compositions, temperatures, processing conditions, and so on. So you only know that there's a partial knowledge of the materials space that is accessible to you, and you really want to go beyond and explore these phases that are unknown. The ways that we usually adopt to perform this kind of exploration is at a first approximation, a free energy model, right? One in which we know that it gives free energy would be a decomposition of an enthalpy and, of course, an entropy term. The enthalpy term can be obtained directly from simulations in these modern methods, the computational methods in general. But the entropy component is a bit more challenging because it requires a lot of sampling. Specifically, if you wanted to know all of the phases that might be accessible in this phase diagram, you're going to have to compute each one of these phases. You're going to have to sample each one of these pathways. You're going to have to understand phase by phase how to perform this exploration. So there's a computing bottleneck here, and this computing bottleneck relates to calculating, understanding, and of course sampling the space of materials systematically and fast. So I would like to build an intuition and go over this presentation with about 3 case studies. And these case studies are going to relate to this keyword of stochasticity that I mentioned in the beginning of this talk. So if we think about stochasticity, we have to always come with the language of probability distributions. In this talk, I'm going to try to build this intuition of materials modeling on top of probability distributions as much as I can. So let's think about a phase space and the probability distributions that can be induced by that. I have 2 probability distributions here, P1 and P2. And P1 may represent our knowledge of this phase space, which is quite limited compared to the actual phase space. P2, that represents the underlying distribution of interest. We know how to sample these pathways. We know how to sample these new configurations, stable states. This is a known process. It's just very time-consuming quite often. So what I can say is that in many cases, only a fraction of the phase space is known to us. how can we make sure that we have predictive models that will always work outside of the phase space that we know? And this is a classical problem that happens from machine learning to atomistic simulations to all of the theoretical principles that we like to think about. And that's what I want to convince you in this presentation, that in order to bridge scales in materials modeling, especially when it comes to synthesis in out of equilibrium conditions and so on, that will require us to understand model generalization, to connect these atomistic simulations to macroscopic theories, and of course, enable faster sampling methods, for example, using generative modeling that might be relevant to material science and engineering. So in one of the recent examples that we have done for the context of electrochemistry relates to coverage-dependent absorption energies in, say, copper facets. You may have any kind of facet, any kind of catalyst, and you know that the absorption energies will be dependent on each one of these coverage regimes that you're at. So in principle, what you could do from a simulation standpoint is you could enumerate all of these absorption sites and brute force through them. Brute force through each one of these molecules absorbing each one of these absorption sites at different coverage regimes and try to hope that that's a good enough of a model. For example, taking all of these surfaces, relaxing them, doing random sampling over this until you reach a certain degree of convergence. But in fact, when we start thinking about a problem like this as a problem of generalization, what you're going to see is that randomly sampling configurations is just sampling configurations that are not the ground state configurations. The configurations that we're actually interested in are those very low energy configurations, because these very low energy configurations contribute exponentially more to your partition function compared to these randomly sampling configurations. Then it's really important for us to have models that extrapolate really well towards these lower energy configurations if all we had is a set of randomly sampled configurations. So there's a key component here that if we're able to construct models that generalize well in some flavor of out of distribution, then we could just use randomly sampled configurations as a training set for a machine learning model and extrapolate or generalize towards low energy configurations in a way that would allow us to sample them much faster using a model rather than, say, more expensive density functional theory calculations, and of course assign a level of confidence to all of that. So there are multiple forms of out of distribution you can consider. Some of the distributions that we have looked at involve looking at in-domain errors, training a model on one facet and generalizing to another facet, looking at training a model into low coverages and generalizing towards higher coverages. And this is particularly interesting because at higher coverage regimes, you end up having a much larger combinatorial space to explore. And of course, you can think about just staggering these coverages and just reducing the phase space that you might be interested in. So there's a lot of tricks in order to improve generalization. We have employed several of these tricks in training graph neural network models based, for example, on the maze architecture. And we have seen that we're able to generalize, go from low coverages or low coverage regimes and make very accurate predictions at a high coverage regime, which is super important because in the end, what we want to do is take these models that are very fast in predicting energies, for example, absorption energies, even in high coverage regimes, and do some extensive sampling, even if it's just very simple Monte Carlo sampling techniques in order to obtain low energy configurations given only randomly sampled energy configurations as initial points, and of course, training data. So it means that we can evaluate millions and millions of structures at over hundreds of thousands of energy evaluations per facet, per coverage, that can later be revalidated systematically. So computing a value of energy for this bottom set of sampled structures is pretty straightforward compared to doing an entire Monte Carlo sampling technique using a density functional theory approach, for example. And when you go back and revalidate all of these approaches, you're going to see that the model indeed performs really well for these low energy configurations, which allows us to go from these atomistic models that can be constructed at very large scales, for example, high coverage regimes at very large lateral cells for each one of these facets, and of course allow us to construct these differential binding energy curves. Now this is nice, right? Because this is something that relates directly to an experimental measurement. You can see when these bends of these differential binding curves happen in an experimental setting. You can compute what are the equilibrium coverages in each one of these regimes and so on for all of these different facets. And you can construct all of that by knowing that your model is generalizing well and by having a pretty good grasp on this phenomenon of generalization. Another harder example you can try to get is, for example, to try to understand CH-OH bond scission co-adsorbed with CO on rhodium-111 facets. We have done exactly the same process, but you can see that now you have co-adsorption, not only adsorption of a single species on this facet. This problem quickly becomes combinatorially more expensive, but again, using the same tricks of increasing model generalization, you can obtain pretty good models that perform very well across coverage regimes, use all of these to sample new data points, and of course, compute reaction barriers under each one of these different regimes. So what I show here is, even if you choose a single coverage, in this case, I think it's about a 50% monolayer, by choosing slightly different configurations, even less than 0.1 electron volt in difference in coverage configuration of energy, you're going to obtain wildly different reaction barriers for the CH-OH bond scission, which is not entirely unexpected. It just highlights how important it is to do this comprehensive sampling and how important it is for us to understand pretty well how co-adsorption will influence reaction mechanisms and all of these reaction barriers that we can sample in this process. This is a single example in which we can just leverage a little bit of generalization and try to understand how to connect it to macroscopic models using a very simple set of atomistic simulations and, of course, very well-defined neural network methods and machine learning methods. But I promised you to talk much more about stochastic methods and probabilistic perspectives on atomistic modeling. Of course, all of this relates to some degree of sampling and probabilistic modeling, but of course, it's just a set of discrete states. You could barely say that they compose an actual continuous probability distribution, and being just composed by final states and understanding them through equilibrium-only states, we abstract away from the interesting dynamics of materials. And these interesting dynamics of materials can be well represented by continuous probability distributions. That is the interesting question now that we can start to think about. For example, if we were able to have access to an actual Boltzmann-like distribution for material systems, what could we do with that? And how would we even be able to access that probability distribution to start with? So it means that when we perform molecular dynamics simulations, for example, we're sampling from this distribution, but we can never see or make this distribution tractable as a mathematical entity, as a numerical method that we can play with. How could we try to do that? Because if we could, in principle, we'd obtain all of the thermodynamic properties of materials that we might be interested in, or most of the thermodynamic properties. So to do that, we took inspiration on this very well-known method by Beller and Parinello to make predictions of potential energy surfaces, right? You probably are very familiar with the idea, but just as a recap, you take each one of these atoms in, say, the condensed phase, you decompose atomic neighborhoods into or these local environments into a particular vector representations using, say, atom-centered symmetry functions, and you use these atom-centered symmetry functions and, of course, these vector representations in order to predict per atom energy contributions, and then these energies, total energies for the system, are just the sum of these per atom energy contributions that are learned using, say, a neural network. The concept here is very simple, but very successful. This still remains as one of the most successful ways to make predictions of potential energy surfaces using machine learning. You go from atomistic structures, you create vector representations, you, from that, use a model, you train a model on particular labels, say from DFT calculations, and you get energies. The question that we wanted to answer with this kind of analogy is, could we do the same for entropy rather than energy? So you see that when we think about probability distributions, and we immediately have to associate that to thermodynamic entropy, right? Because that is the quantity that relates to sampling. That's the quantity that relates to the uncertainty in the microstates that you have accessible in your system. So our trick to start creating probability distributions out of molecular dynamics trajectories or out of any kind of trajectory you might think of relates to this. It's still the same picture, one in which we decompose a structure into atom-centered representations. And from this structure, we create a collection of these atom-centered representations. And from this collection of atom-centered representations, we can create a non-parametric distribution, probability distribution then that comes from this space of representations. If you have a probability distribution, then it's straightforward to compute the value of an information entropy from that. You can notice that this is not a thermodynamic entropy, and it's probably never going to be an actual thermodynamic entropy, but it's an information entropy. And this particular information entropy is something that emerges from atomistic structures. When you take their structures, create vector representations in an atom-centered representation way, and from that, you use a kernel density estimate, very simple approach to create a probability distribution, and get from there an information entropy. So now what I'm saying is that I started with a structure, and I created a quantity, a probability distribution, and a quantity associated to it, which is the information entropy. Now, what can I do with it? And what is even the intuition behind an information entropy for materials modeling? Well, I like to show this example of how information entropy can be somewhat intuitive when you take an example of a known probability distribution, such as a coin flip. In a coin flip, you have a 50-50 chance of landing heads or tails, and you can create, of course, a probability distribution for that, which is just a point mass distribution with two different states. And with this probability distribution, you can compute a value of information entropy. The information entropy of that, if you take the log in base 2, is going to be exactly equal to 1 bit. So it's not surprising to anyone that the amount of information contained in a coin flip is exactly 1 bit. But this mathematical formalism of mapping from a probability distribution to the exact amount of uncertainty or information contained in this coin flip is extraordinary, because it allows us to take in any probability distribution and move away just from this intuitive understanding of entropy as an uncertainty on the microstates to something we can quantify. We quantify it through the surrogate of information theoretical analysis. And the information theoretical analysis then allows us to build more of this intuition of the higher the spread of a distribution, the more uniform is the distribution, the higher the information entropy. And of course, you're going to have a couple of very well-defined states. When the information entropy of the system is equal to 0, then you have a deterministic system. There's absolutely no uncertainty about the outcome of that process. And if you have a uniform distribution, then your entropy is maximized because you have you have maximum uncertainty about the outcome of your system. So this is the method we started thinking about in order to involve a little bit more of this stochastic or probabilistic perspective on materials modeling. One in which we can go from atomic environments, decompose them into fast representations, compute non-parametric estimates, and from there get to a value of information entropy. And of course, you can implement all of that to be very, very fast, because especially computing these kernel matrices is something that can be pretty computationally expensive. Using this formalism, we have applied the idea of information back to these ideas of generalization that I mentioned before, but also to a range of other materials modeling techniques. For example, you use that to rationalize extrapolation, measure active learning performance in machine learning interatomic potentials, compress data sets, model nucleation and growth, think about phase diagrams and even vibrational entropy components of that, and even detect failed simulations. So I would like to, of course, we're not going to go over everything, but I would like to talk about two of my favorite examples in this. One of them being data set compression. You know that when we want to train machine learning interatomic potentials that are super relevant for a range of the applications that we might be interested in, there are a lot of problems along the way, right? You never know how much data is enough, if your data set is diverse enough. A lot of different efforts, including from Danny at the back, have been extremely successful in generating very diverse data sets and really creating something that can serve as a good starting point for machine learning potentials. But more broadly, this is still an issue we face every time we train machine learning potentials. But even after you train, you have problems with uncertainty quantification. You have problems in detecting outliers and thinking about robustness of these machine learning interatomic potentials. And even after performing simulations, you might want to do an active learning loop in order to increase the convergence and sampling efficiency of all of that. Importantly, in this main pipeline of training models, you have to answer this question of data set completeness and model errors. overall. The typical pathway to do that is the machine learning pathway of adding more data, right? The more data you add to your training set, the lower the errors and the better the performance of the model in general, including in generalization, which is great. But how do you explain each one of these learning curves? How do you explain this kind of phenomenon from a materials science perspective? Well, the way that we adopted to explain this, that more data will reduce these errors, is one that comes from the phase space of materials themselves. By computing the amount of information contained in each one of molecular configurations, atomistic configurations, you name it, you can compute how much information do I lack with respect to the infinite data set limit. So it means that I can take different molecules, perform molecular dynamic simulations, and subsample these simulations, unbiased simulations in general, in order to see how much of the entire phase space have I captured in this simulation, and plot this amount of information as a function of the number of samples. This plot here is not going to be extremely surprising to you. Benzene is a very redundant molecule, 6 redundant hydrogen atoms, 6 redundant carbon atoms, and very rigid as a molecule. So it's not surprising that very quickly you saturate the amount of information you get from that particular molecule. However, if you increase the complexity of the molecule, for example, azobenzene, still redundant, but less redundant than benzene itself, aspirin, much less redundant than all of them, with more rotatable bonds and so on, you're going to see that the amount of information contained in a data set, even with tens of thousands of samples, is not enough to completely saturate your knowledge of that potential energy landscape or your knowledge of that phase space. And this is extremely relevant, because when you compare this information gap, or how much information do I need in order to maximize my knowledge of the system, against the error in forces of all of these typical machine learning potentials, you're going to see a very strong correlation between that. This is incredible, because at 0 points, I talked about creating a model here. At all times, all I did was to measure the amount of information in a data set without requiring any model. And the y-axis over here requires extensive model training, extensive utilization of GPU resources, and so on. So what this is saying is that perhaps the error in the generalization or in the errors of these machine learning potentials in general can be represented by this universal quantity, which is how much information do I actually miss when I reduce data set sizes. To demonstrate that this is not restricted to molecular systems, you can try to do the same thing for, say, the GAP20 dataset that exhibits a lot of carbon polymorphs, and start to rationalize the trends among different polymers. Not surprising again, you're going to see that liquid and amorphous bulk will have high information entropy and low levels of redundancy, especially because the data set itself has been subsampled by the authors of this work. But of course, you would expect liquid to have much more information compared to just graphene, right? And that's exactly what we find. Interestingly, because information theory has a maximum amount of information you can contain in a certain number of samples, we can see exactly how much redundancy exists in each one of these data sets. Look at the size of this gray bar here and compare it with the size of the blue bar. The size of the blue bar is the actual amount of information contained in that data set. And the size of the gray bar is the entire size of the data set. So the longer this gray bar over here, the more redundant information we're adding to our train set, which can represent in a way or another just spent computational resources in looking at the same structures over and over and over. So what can we do in order to address this particular problem? Let's make a very simple example. Let's take graphene over here and fullerene. You can see by the length of these bars that they have different amounts of redundancies. So what I'll do is I'll randomly sample each one of these data sets and train a model on the randomly sampled data set and compare against the model trained at 100% of the data set. When I do that, and when I do that for graphene, you're going to see that the amount of information gap, that quantity that I defined before as how much information we're missing from my system, remains very close to 0, but it increases quite rapidly for fullerenes. It means that by subsampling the fullerene data set of this GAP20 data set, we're removing a lot of information. And indeed, that relates to the increase in the model error as I reduce training set sizes for this particular subset. This is not the case for graphene, as you can see over here. So this is interesting because information theory information entropy is this metric that indicates compressibility of data within the field of information theory, which is, by the way, what enables all sorts of data communication in the world that we have right now. But here I'm making a very simple assumption, which is just by randomly sampling data, I can immediately compress a data set. This might not be the most efficient way to subsample your data set. So recently, with a very talented undergrad here at UCLA, Ben Yu, we've been looking at different algorithms on how to compress these different data sets. For example, you can just try a simple random sampling, but you can also do some flavor k-mean sampling. You can do mean farthest point sampling, and of course, some more sophisticated methods to compress these data sets. And interestingly, information theory is the field that allows us to quantify how good is a data set when compressed, or how much information do we actually miss when doing that. Our algorithm is this one that we call the minimum set coverage because it tries to maximize the coverage of your entire phase space with the minimum set of structures. We have shown that within these results, our algorithm that's shown here with this dark line tends to always maximize the entropy while keeping the diversity of their data set as large as possible. Over here, what you're seeing is that I go from 100% of a data set all the way to 10% of the data set size along each one of these lines using these different methods. You can see that if I try to just randomly sample the structures, I start losing information and diversity of the data set almost instantly. But according to algorithms such as ours, we can keep maximizing the amount of entropy that I have in my system, so I'm reducing the redundancy while keeping the diversity as high as possible. When you look at the overlap of the compressed data set with respect to the original data set, you're going to see extremely good performance, again, using methods such as the minimum set coverage like ours. And of course, that doesn't restrict itself to the GAP20 data set. In fact, we looked at 64 different data sets and performed the same compression experiments across 75, 50, 25, and 10% sizes. And we saw that minimum set coverage outperforms all these other compression methods in the majority of cases. So this is very cool, right? Because beyond just saving computational resources and training your models, beyond just removing redundancies from them, now we're learning something about the phase space. And learning something about the phase space is something that connects very well to these continuum models that we might be interested in thinking in this workshop. For example, another one of my favorite examples of this involves the ideas of nucleation and growth. And nucleation and growth, if you're dealing with, for example, electrochemistry, in which you have interfaces, especially between solids and liquids and electrified interfaces that may make that much more complicated, that is quite similar to some of the problems faced in synthesis of materials, especially from this nucleation growth perspective. If you look at classical nucleation theory, you're going to see that in classical nucleation theory, you expect distributions of clusters with different sizes, and this cluster size distribution follow more or less this law and this curve over here. Another one of the problems that we see in synthesis of materials in nucleation theory is this question on whether certain mechanisms of synthesis follow a two-step nucleation process, one-step nucleation process, non-classical pathways, and so on. For example, through aggregation of local densification of clusters before actual crystallization. But then all of these questions beg other additional questions such as how do you even define a cluster? What is this densification? What is even a cluster size distribution if you don't know how to define what a cluster is? So we wanted to give an example on that and how that relates continuum models such as a classical nucleation theory or very generalized approaches to understanding mechanisms of nucleation if we can't define this at the atomistic scale. So it means that we need tools to connect the atomistic model to the continuum model. To exemplify this, what I did here is perform the simulation on solidification of copper. So you have copper at a particular undercooling, about 400 Kelvin of undercooling, and it undergoes a transformation from a liquid phase to the solid phase. The solid phase, shown here in green, is essentially just an FCC phase with HCP stacking faults shown in red. So this is a classical mechanism for homogeneous nucleation, right? You have liquid to solid phase transformation, and in principle, you would say, oh, I'm going to be able to capture all of those clusters and the cluster size distribution that I mentioned before. However, if you use typical algorithms to classify local environments, neighborhoods, such as the adaptive CNA or many others even, you're going to see that these methods of classification can't really define what a cluster is. Within adaptive CNA, what you're going to see in the trajectory I showed just now is that the maximum cluster size from this method is 1, at most. In most cases, the maximum cluster size is 1 until it's actually solid. Then the algorithm starts to detect that. This is not exactly what we expect, right? The continuum type of approach expects a distribution of clusters in the melt, and the distribution of clusters should obey more or less what we see in classical nucleation theory. This is definitely not the case over here. So how do you even define clusters using this perspective? Or in our information theoretical perspective, what we did is we defined a cluster as the region of the liquid that contains the most mutual amount of information, so to speak, with respect to the solid. Or alternatively, the parts of the solid that can be found in this continuous probability distribution space of the liquid in order to define a cluster. And if you adopt this strategy of using these probability distributions and overlaps between probability distributions to identify clusters, suddenly everything comes into the right place. You can start seeing clusters that weren't identified by adaptive CNA or other algorithms. You start to see cluster sizes distributions that make sense. The largest cluster size fluctuates around the sizes that we expect for that particular undercooling. And this range of clusters sizes over here are ranges that correspond to experimental values of what is the maximum or the minimum cluster size that will lead to nucleation. And indeed, it crosses, or cluster size distribution crosses this boundary in 2 places. B over here, which ended up being an artifact of one of the methods we used to select clusters, and C as being the actual critical nucleus that leads to nucleation, to the nucleation event of this. So interestingly, what we're doing here is we're looking at systems from an atomistic perspective, but connecting it back to continuum models that relate to classical nucleation theory. And indeed, it wouldn't be so straightforward to compute this delta G of transformation from solid to liquid, or liquid to solid transformation, or the interfacial energy. But if we have cluster sizes distributions that are pretty reliable, as we have now, then we can extract these values straight from a typical classical nucleation theory fit that leaves us with the data. So again, just by adopting this probabilistic perspective on what is a solid, what is a liquid, and how to define clusters in it, we're able to recover a continuum model that wasn't accessible, totally accessible from an atomistic perspective. So information theory now, information entropies, not only allows us to understand data set compression, or not only allows us to understand these probability distributions in general, but also recover some of these continuum models that we might be interested in. Now, this is great, right? Because we have a powerful tool to explore and understand probability distributions overall. Now that we have analyzed these probability distributions, we feel more or less confident that given a simulation, a trajectory, for example, we're going to be able to extract a probability distribution from that, and from this probability distribution, quantities such as information entropy and so on. Now, sampling distributions, however, is another problem that we haven't talked about. We know that we want to have knowledge of the full phase space, and the entire distribution takes a long time to sample. It will likely take us the largest amount of time in this entire study. It would be wonderful, however, if we could simply sample trivial distributions, like a Gaussian distribution, and map it back to entire new distributions that we don't have, or we don't have access in a most tractable way. So this relationship between mapping distributions would be extremely powerful to keep sampling these new states, which can be pretty complex, but we might be interested in overall. And that's essentially the formalism of generative modeling, right? We have seen generative modeling taking the world by storm and looking at generation of text, language, images, and whatnot. And the powerful approach about that is you can start from random noise, and using this Markov chain, for example, you can just go from pure noise into an image that resembles the actual image sampled from the original distribution of all images that's unknown and intractable to us, but that can be learned by the model. We have been seeing all of that also reaching the field of material science and engineering, molecular structures for a longer time, but by mapping from randomly placed atomic configurations into stable inorganic crystal structures, such as in this work from Tien and the Microsoft team. So the question that we might be interested in asking is, if we moved away from simple, well-defined inorganic crystal structures and towards complex interfaces, structures, amorphous materials, liquids that we might be interested in and might be of relevance for the field of electrochemistry as well, we have to ask ourselves this question: how do we actually generate these statistical distributions of complex atomistic systems, such as amorphous materials, interfaces, and so on? So this is what we've been working on in the last year or so. Kai, who just graduated as a PhD student but is now a postdoc in my group, he developed this diffusion model for amorphous configurations. In principle, what you could do is you can sample atoms according to a uniform distribution in a box and start removing noise from these atoms in such a way that they resemble an amorphous configuration. An amorphous configuration is not like a crystalline configuration in which you would be able to assign a very well-defined loss function to that inorganic crystal structure. An amorphous configuration can have multiple different configurations that follow the same short-range ordering. So the trick here is to find out how to sample amorphous configurations, how to define stability of amorphous configurations, how to define uniqueness of these amorphous configurations, how to define whether the generative model is actually producing novel configurations. So all of these patterns of defining what is stable, what is unique, what is novel is quite ubiquitous in generation of crystal structures and generation of molecules or so, but it's not trivial at all in the generation of amorphous structures, interfaces, and so on. So what we did in order to resolve that is we trained this diffusion model using amorphous materials as the training data. We sampled these amorphous materials using classical molecular dynamics simulations, and within these atomistic simulations, just using a simple melt-quench process, you can end up with some training examples of amorphous configurations. A denoiser model essentially is trained to remove noise from a structure, and the noise is added at train time. So pretty straightforward to train in that perspective. And the denoiser model can make use of even equivariant graph neural networks in order to learn the direction of these, the added noise and so on, and it makes it very easy for us to define a loss function for that. The trick here is not only how to train this model, but also how to generate new configurations from random distributions. What we did in this model was to take randomly sampled atoms as initial configurations, but we also trained the configurations according to processing conditions, such as cooling rate, the cooling rate that we used to generate this particular configuration. And at inference time, that's going to become the target cooling rate of that particular distribution. That goes into the denoiser model that in an iterative process starts removing the noise from the system and gradually reaches something that resembles an amorphous configuration. In the end, if you want to compute properties, if you want to do MD, you can do it using these generated configurations without having to go through the entire sampling process of melt-quench like you would do in a typical simulation. We noticed that by doing this process, by doing the conditional generation and so on, these diffusion models excelled at sampling amorphous materials. This is an example of amorphous silica, which is a very well-known case in which amorphous materials are studied. And here is an animation where we go from random noise into amorphous configurations. Amorphous configurations cannot be defined uniquely as the inorganic crystal structures, but we can see that the generated structures reproduce very well the short and medium range order of all of these amorphous configurations as defined, for example, by these partial PDFs. But you can look at many other things, and we looked at bond angle distributions, ring size distributions, and all of them reproduce very well the reference data sets, despite being complicated, complex amorphous configurations. One of the interesting results that we see from that is that elastic properties of these generated structures, when you actually use generated structures for downstream simulation tasks, you see that the elastic properties are nearly indistinguishable or statistically indistinguishable from the original structures that have been used in the simulation. So this is excellent because when we talk about outliers in the generation of structures, they should be influencing quite a lot these mechanical properties. You wouldn't see outliers very well in partial PDFs such as this one, but you would definitely see mechanical properties that are nonsense if you have several outliers environments or even one single outlier environment in this particular system. And yet, when we look at these mechanical properties, we define something that's very strong and says that beyond reproducing just structures of materials, we also reproduce their properties, which is extremely relevant when sampling these configurations. More importantly, if you're familiar with this field of amorphous materials, interfaces, and complex materials in general, you're going to see that there's a big divide between what we can do in simulations and what we can do in experiments. In the case of silica, for example, the cooling rates that we often use when performing simulations in these systems are extremely high compared to experimental cooling rates, which are in the orders of Kelvin per second. We can never simulate seconds of molecular dynamics simulation, so we often perform these cooling rates over picoseconds, right? So how do you actually bridge this divide between an experimental processing condition and what we can start to do in a simulated processing condition? Well, remember that knob we added in terms of conditioning the generation of materials to the amorphous materials to their processing conditions, such as cooling rates? Turns out that we can show that our model produces structures at the right densities, at the right values of information entropy in this according to a certain cooling rate. So if we generate materials conditioned on higher cooling rates, we end up with structures that exhibit higher amounts of information entropy. And if we condition the generation of amorphous materials to lower cooling rates, you're essentially just reducing the amount of information entropy contained in that system. And again, information entropy is a very useful quantity because it really allows us to measure the amount of diversity and the amount of redundancy in these configurations across cooling rates as well. Very much like you would see in these typical textbook examples of glassy materials being cooled. That also reproduces other factors such as short-range ordering parameters that we often see across cooling rates in silica glass, with some very useful generalization trends in this system. You can see that even though we have not trained the model on very low cooling rates, like 10 to the minus 2 Kelvin per picosecond, the model generalized pretty well alongside this direction. And importantly, when you look at this data point over here, you're going to see that the lower the cooling rate, the longer the simulation you're going to have to perform in order to get to the final structure. However, a generative model can generate that at constant time, at a constant number of steps. And at the low cooling rates, the gains in computational wall time you would expect can reach 3 orders of magnitude. And that, of course, would improve even more if you go towards lower and lower cooling rate, provided that the model would generalize well. The advantage of doing that is that now I can sample very structures that have been generated with very low cooling rate and perform larger simulations. For example, fracture simulations. Instead of doing the entire melt quench process in order to just get a large simulation with hundreds of thousands of atoms, now we can simply generate a box with randomly placed atoms, hundreds of thousands of atoms, millions of atoms, and denoise them in order to form an amorphous structure that's pretty plausible. And when you do that, you also recover all of these trends in stress strain that you would observe in the literature of glassy materials simulations. And this is important, right? Because we want to go towards continuum type of models. We don't want to capture only the ductility of silica at the small scales, but we might want to be studying effects of embrittlement and many other parameters at larger scales. What else can we do with this? Well, if I can sample anything I want, any kind of box that I want, I can try to sample boxes that have special conditions. For example, mesoporous silica is super important as in applications from catalysis to drug delivery. But from a simulation standpoint, it's not as simple to sample an amorphous mesoporous silica. So one of the things that we did is, even though we did not train the model or any kind of surface or any kind of configuration that resembles an interface, we managed to denoise a configuration from randomly placed atoms with the exclusion of a cylindrical volume here in the middle, all the way to an amorphous configurations that, again, reproduces the short and medium range order of amorphous silica. And you can even see here that on the surface of this pore, you're going to end up with these non-bridging oxygen atoms that eventually will become silyl groups if you're modeling, for example, phenomena in catalysis, interfaces, and so on. Again, we studied this in a lot of detail. We looked at metallic glasses just to show that this is not just applicable to network glasses, silica, and so on. We've done that for metallic glass and also some experimental glass systems, and we see the same result. We can go from randomly placed atoms and configurations, reproduce short and medium range order in these materials, and continue on with the development of new models, continue on with the simulations of these systems at different scales that previously were not entirely inaccessible, they were just inconvenient to keep simulating over and over and over. However, if you have a tool that allows you to bridge across scales, bridge across length scales and time scales all together, then we're going to be able to do very interesting things regarding materials modeling and simulations in general. So this is where I wanted to conclude this talk. Again, going back to this point of bridging scale in materials modeling, I'm particularly interested in synthesis science, of course, but in general, in this field, that requires several advances in understanding model generalization, because most of the problems we're going to be dealing with involve generalization, rare events, interfaces. Those are things that we most likely than not will not be sampling in a training data in the most comprehensive way. We have to think about how to connect these atomistic simulations with the macroscopic theories, just like we did with this probability distributions standpoint, going from atoms and clusters to classical nucleation theory, and of course, finding out methods on how to accelerate that, for example, using generative modeling that might be relevant to materials science. So with that, I wanted to conclude this talk by thanking, of course, a lot of our collaborators at Lawrence Livermore National Lab with whom I collaborated a lot in some of these projects, my group at UCLA, and of course, several of our funding sources, especially here from DOE and TRI. Thank you very much.